In Module 6, we're going to take a look at right triangles. But before we do that, we're going to talk about geometric mean in Section 1. So to start off, we're going to talk about the parts of a right triangle. So we obviously have our right angle, and then the other two angles within that triangle are acute angles. They are less than 90 degrees. We also have the two legs of our right triangle, which are going to be the sides next to the right angle. And then we have the hypotenuse. And the hypotenuse is always opposite the 90-degree angle. So when we're looking at a right triangle, our hypotenuse is always opposite the 90-degree angle. We also can draw the altitude of a right triangle. So that is a separate segment that forms a right angle with the hypotenuse. And when we do that, we get these special relationships that exist, which we'll be talking on later on. We still have our two legs, but that altitude that we draw to the hypotenuse creates these two segments along the hypotenuse. And we're going to be talking about that, as I said, later on. A nice little piece of information about right triangles is that all right triangles are isosceles or scalene. So what that means is the two legs are either going to be the same length and the hypotenuse is different, or all three sides of the right triangle are different. No right triangle is going to be obtuse, acute, or equilateral. It's just not possible. So let's first talk about a theorem that we have that says that if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So we're going to take a look at this example where AD is the altitude of triangle ABC. We want to name the three similar triangles. So let's start with our original triangle, ABC. It is the larger triangle, which is what L stands for. Next, we want to take a look at the middle triangle. So the middle triangle is this first one that's inside. So when we go to name it, we want to make sure we name it in the same way that we named our larger one. So our larger triangle, we started it at the point for the right angle. We went along the shorter leg and then down the hypotenuse. So we want to do the same thing for our medium triangle. So point D is where we start with the right angle. The shorter leg is along A, and then our hypotenuse goes to C. And then we have the smaller triangle. So when we go to name the smaller triangle, we want to follow the same lines. We want to start at the right angle, which is still point D. We want to go along the shorter leg, which is to point B, and then across the hypotenuse, which is C. So the three right triangles we have are triangle ABC, our original, and then our two smaller triangles DAC and DBC. Now we can write similarity statements for the similar triangles. So the first thing is we know that the smaller triangles are similar to our original triangle. So we know that ABC is similar to both triangles DAC. And then we can also say triangle ABC is similar to triangle DBC. Okay. We also know that the two triangles formed are similar to each other. So my last statement is then going to be that DAC is similar to DBC. And I should have my little triangle symbols in front of all of these because we are talking about triangles here. So we have three different sets of similarity statements for all three triangles. Next, we're going to talk about geometric mean. So the geometric mean of two numbers, a and b, is the positive number x such that a over x equals x over b. So in our first example, we want to find the geometric mean of 3 and 10. So we can let a equal 3 and b equal 10. So we have 3 over x equals x over 10. And then we're going to cross multiply. So we get x squared equals 30. And then to get rid of that squared, we take the square root of both sides. So we get x equals the square root of 30. And using a calculator, we get an approximation of 5.5. So now we want to find the geometric mean of 2 and 18. So we can let a equal 2 and b equal 18. Now it doesn't matter which one you choose to be a and which one you choose to be b, but typically the first number is a and the second number is b. So we set it up into our formula. We have 2 over x equals x over 18. And again, we cross multiply. And we get x squared equals 36. And this time when we take the square root of both sides, we get x equals 6. Because the square root of 36 is 6. So the reason why we talk about geometric mean is it helps us solve right triangles. So in a right triangle, the length of the altitude from the right angle to the hypotenuse is the geometric mean of the lengths of the two segments of the hypotenuse. So if you remember from the first page when we drew that altitude, we created our two segments and we had our two legs. So if we let S1 and S2 be our segments, and we let A be the altitude, we end up with the formula that S1 over A has to equal A over S2. So it's basically taking that geometric mean formula and replacing S1 and S2 with A and B because those are the two segments of our hypotenuse, and instead of X, we have the altitude A. So go ahead and use this in an example. So we have our right triangle with our altitude X and our two segments 10 and 6. So we can let 10 equal S1 and 6 equal S2. So in order to solve for X, we're going to set up the geometric mean. So we know S1 over A is going to equal A over S2. When we know the length of one of our segments is 10, our altitude is X, so we get 10 over X equals X over our second segment, which has a length of 6. So again, we're going to cross multiply, so we get X squared equals 60. Take the square root of both sides, and we get X equals the square root of 60, which when plugged into a calculator gives us roughly 7.7. So the geometric mean, the length of my altitude, is the square root of 60, which is about 7.7. We also have a theorem that states that in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. Each leg of the right triangle is the geometric mean of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. So again, from that first page, we have L1 and L2 that are the legs. We have the S1 and S2, which are our segments, and we have H, which is the hypotenuse. So we end up with two different geometric means here. The first one having to do with leg 1. So we have that it's the geometric mean of the hypotenuse and the leg adjacent to it. So if we're talking about segment 1, hypotenuse over segment 1 has to equal, we're talking about the geometric mean of the leg. So the hypotenuse over leg 1 has to equal leg 1 over its adjacent segment, which is going to be segment 1. We can also do the same thing for leg 2. So the hypotenuse over leg 2 is going to equal the length of the leg 2 over its adjacent segment, which is going to be S2. Again, I'm getting all of these variables from the picture on the front of your notes where we labeled our right triangle. So if we're looking at example 5, we're not going to solve it, we're just going to identify the adjacent information. So the segment of the hypotenuse that is adjacent to leg AB, that is one of our legs. So adjacent means next to. So if I identify leg AB, the adjacent segment to the hypotenuse is the one next to it, which is BD. And then the segment of the hypotenuse that is adjacent to our second leg, which is leg AC. So the segment of the hypotenuse adjacent to AC is going to be DC. It is easier to see this relationship from a picture instead of just talking about it. So adjacent is the part of the hypotenuse that touches that leg. So now we're going to use these different equations in some examples. So our first example, we have the altitude with length x and the two segments of our hypotenuse 18 and 8. So we're going to use that first geometric formula that has to do with the altitude. So we know that the segments over the altitude, so 18 over x, equals the altitude over the other segment, which is 8. So we're going to cross multiply, and we get x squared equals 144. We're going to take the square root of both sides, and we get that x equals 12. Example 7 is going to be the example of the most recent geometric mean, when we're talking about finding the length of one of our legs. So we know that it has to do with the hypotenuse. So we know each segment of our hypotenuse is 9 and 3, which means the entire hypotenuse is 12. So we have 12 over the leg we're trying to find, which is x, equals x over the adjacent segment, which in this case is going to be CD, which has length 3. So again, we cross multiply, we get x squared equals 36. And then we take the square root of both sides, and we get that x equals 6. In example 8, we're solving for two variables. We're solving for x and y. I'm going to go ahead and solve for x first. So that involves using the formula we just did. So the length of the entire hypotenuse, 48, over the leg we're trying to find x, equals x over the adjacent segment, which is 3. Cross multiplying gives us x squared equals 144. We take the square root of both sides, and we get x equals 12. Now, in order to find y, we use the first formula we talked about having to do with the geometric mean involving the altitude, which means we need the lengths of both segments. So if the entire hypotenuse is 48, and one of the segments has a length of 3, the second segment has a length of 45. So when we set up our second geometric mean, we're going to have 45 over y equals y over 3, which is our second segment. Cross multiplying gives us y squared equals 135. Take the square root of both sides, and we get y equals the square root of 135, which, using a calculator, is roughly 11.6. In example 9, we have the altitude, and we want to find one of the segments. So we're going to use that first geometric mean formula. So we have 16 over our altitude 12 equals 12 over our second segment x. We're going to cross multiply, so we get 16x equals 144. We're going to divide both sides by 16, and we get x equals 9. Number 10, we're solving for three variables. We're solving for x, y, and z. And it's going to be easier if we solve for x first, because that is part of one of the segments of our hypotenuse, and we know the length of our altitude, and we know one of our segments. So setting up using that first ratio, we have the length of our segment, 24, over the hypotenuse, 12 square root 5, equals the altitude, 12 square root 5, over our second segment, which is x. Cross multiplying, we get 24x equals, and then we do 12 square root 5 times 12 square root 5. If you use a calculator, you will get 720. Divide both sides by 24, and we get x equals 30. I'm going to go ahead and label that in our picture. Now we're going to use our second geometric means to help us solve for our legs, y and z. So solving for y first, we know that the hypotenuse, so because we now know x is 30, the entire hypotenuse is 30 plus 24, which means the entire hypotenuse is 54. So when we set up to solve for y, we'll have our hypotenuse, 54, over y equals y over the adjacent segment, which is 24. Cross multiplying, we get y squared equals 1,296. Take the square root, and we get y equals 36. Now to solve for z, again we use the length of the entire hypotenuse, 54, over the leg z, equals z over its adjacent segment of the hypotenuse, which is x, which we've already solved for and is 30. Cross multiplying, we get z squared equals 1,620. Take the square root of both sides. We get z equals the square root of 1,620, which is about 40.2. Last example, example 11. We want to find one of the legs of our right triangle, and we only know the lengths of the segments of our hypotenuse, which means using our second geometric mean. So we need to know the length of the whole hypotenuse. So if one segment is 18 and the other one is 5, the whole hypotenuse has a length of 23. So we have 23 over x equals x over the segment that's adjacent, which is going to be 18. Cross multiplying, we get x squared equals 414. Take the square root of both sides. We get that x is the square root of 414, which is approximately 20.3. So I know geometric mean can be a little bit confusing, but all it is using is setting up the proportion for the corresponding sides of the similar triangles. That's how we get geometric means. It's because all of those right triangles are similar. The geometric means is just the proportion of the similar sides. It's just easier if we just create a formula for it instead of trying to figure out which are the similar sides every time. So let me know if you have any questions as you're working on your assignment.